This is Suvarchala, working as an associate professor, Department of Computer Science and Engineering at Institute of Aeronautical Engineering. As a part of the design and analysis of algorithms lecture series, today I would like to explain about performance analysis of algorithm. So in this video, we would like to include performance analysis related to space complexity, time complexity, and introduction to asymptotic notations. So as we discussed earlier, before writing any program, an algorithm has to be written as a planning so that if a particular problem able to get solved or a solution is feasible solution is available or not, to check that we need to write or we need to take some tool. Algorithm is such a tool actually. So an algorithm is an exact specification of how to solve a computational problem in terms of steps, and also we discussed already about the characteristics of the algorithm also in the previous session. Now, an algorithm must specify every step completely so that computer can implement without any further understanding, and also it must work for all possible inputs of the problem. An algorithm must be correct as well as efficient, and to solve any problems depending upon the logics developed by various techniques, various algorithms can be written by us actually for the same problem. So an algorithm is sequence of unambiguous instructions for solving a problem so that input will be the given and a problem as given. An algorithm is written and we are going to trace the algorithm, what type of output we are going to get actually. So to get the required output and proper input is going to be provided so that in finite amount of time, the input must be converted into output as per the logic of the program. Simple example we will consider. So GCD. So where we would like to find GCD of any two numbers, two positive integers. So one example is GCD of 60, 24, a normal example. So we will divide 60 by 24. So we will get a remainder as 12, and we'll take now 12 as a GCD will be considered. Similarly, GCD of 60, 0 is 60, and so on and so forth. Euclid's algorithm is based upon the repeat application of our GCD is going to be computed equally as GCD of Mn is equal to GCD of n comma m mod n, that is remainder, until the second number becomes 0. So that means if second becomes 0, remainder is 0 means if the problem is trivial, whatever the divisor is, that is GCD. So GCD of 60, 24 is resulted as GCD of 24, remainder, that is 12. And GCD of this 24, 12 is GCD of 12, 0. We will stop. So what is the GCD? GCD is 12 actually. So like that we are going to find GCD. How to write an algorithm for this finding GCD? Various methods can be adaptable by us actually. First method, consecutive integer checking algorithm. That is, we are going to assign the value of minimum of mn to a variable t, divide m by t so that we will get the remainder. If the remainder is 0, we will stop and we will return the t value as a GCD. That is, go to step. We are going to, if the remainder is 0, go to step 3. That is, divide n by t. If the remainder is 0, return and stop. Otherwise, go to step 4. So what we are going to do here? So when we are dividing m by t and n by t, we are coming back to the respective by decreasing t by 1 and go to the step 2. So this process is continued. That means continuous divisions of m and n by t minus 1. Other method is there actually. This is common method. Generally, we will use in our school days. That is, we have to write all prime factors for m, all prime factors for n, and common prime factors we are going to be selected. The product of these common prime factors will be the GCD of these two numbers. This is another technique actually, right? So, like that, to solve a problem, various methods will be there, or various types of algorithms can be written by us, and we have to solve our problem. Solving a problem is not getting just mere result or output to that particular problem. We have to solve a problem with a more efficient manner. That means the efficient manner means whichever the algorithm we are writing for solving a problem, that algorithm must be more efficient. What is efficient actually? That means just non-ambiguity requirement, each step of an algorithm cannot be compromised, and the range of inputs are also we have to check. Our algorithm should work for all ranges of inputs. And as I told you, same algorithm can also be represented by using various techniques. And several algorithms will be there for solving the same problem. Just now we discussed for finding the GCD. Various algorithms will be there. So the algorithms for the same problem can be based on various different ideas and can solve problem dramatically with different speeds also. Now our question is, which algorithm has to be selected by us actually? How do we compare algorithms? We need to define the number of objective measures. That means the parameters. We have to consider some parameters based upon which the algorithms are going to be compared so that the best algorithm can be chosen by us actually. So what are those objective measures can be considered? Is it execution time? But execution time is not good. Why? Because depending upon the machine's particular computer, the execution times are going to be changed. So we cannot consider the execution time as this, as one of the measure actually. Count the number of the statements, second one, right? So it is also not good. Why? Because depending upon the programming language, the number of statements are going to be get reduced. For example, for solving a small problem, in case of COBOL, if you are going to write almost 40 to 50 lines program, in case of Fortran, some lines, in case of C, now if you are going to consider in case of Python, even 1 or 2 lines, also it's enough for us actually. So depending upon the language, the number of lines are going to be varying. So that's why this is also not considered as a good measure or good parameter to compare our algorithms actually. So that's why express running time as a function of input size. So we have to consider our time taken to solve that particular algorithm as a function of input size. Depending upon the size, how the time taken to that particular algorithm is going to be changing. Depending upon that, comparison can be done. So the compare different functions corresponding to the running times based upon our input size, then it may be a little bit considerable measure actually. Such analysis is independent of machine time and programming style, etc. So when we are going to consider our algorithm analysis, what is meant by analysis of algorithm and why we should study algorithms and their performance? Already we discussed the reason. Because the performance analysis is required to compare our algorithms. Why? Because to solve a same problem, a number of algorithms are going to be available to us. We have to choose the best one. How to choose the best one? Depending upon this analysis actually. So what is meant by performance analysis? Generally, performance analysis often draws the lines between what is feasible and what is impossible. Generally, when we are writing an algorithm, we able to analyze, we able to specify whether that particular algorithm provides a proper solution or not, exact solution or not. And also algorithm mathematics provides a language for talking about the program behavior also. And the program performance generalize the other computing resources. So that's why speed is going to be considered as one of the analysis factor of a algorithm actually. That means the theoretical algorithm is theoretical. The algorithm cannot be implemented as its own system. It has to be converted into a program. Program means algorithm implemented in any high-level language is considered to be as a program. So the theoretical study, that means it's not implemented on a system. So that's why the time taken by a system is not at all considerable here. That is, prior analysis is there. Algorithm analysis is prior analysis. And program analysis is posterior analysis actually. So the theoretical study of the computer program performance and resource usage is considered as an analysis of algorithm. But remember, always just considering our algorithm, that is whatever the measures we are going to consider, either a time or a space, etc., etc. Other than that, we need to consider the performance analysis based upon the other factors also. But these other factors are not considered explicitly actually. That means the modularity, correctness, maintainability, functionality, robustness, user friendliness, programmer time, simplicity, extendability, and reliability. All these factors need to be considered by us actually. But remember, all these factors are going to be considered as a secondary thing. Primary issue is while considering the best algorithm, of course, any algorithm has to follow all these characteristics must hold good. Along with that, whichever algorithm is providing the best algorithm means it's time taken to run that particular program or tracing that particular algorithm, time taken to solve that particular problem, as well as the space related to that particular solving the problem is considered as the major measures. That means I have to evaluate algorithm. No? That means judgment must be considered by us. So judgment here in the evaluative judgment is going to be based upon the predicting the resources which are required for an algorithm can be considered actually. That is to perform a task, what are the resources are required and how the resources are going to be used more efficiently, that will be considered. That means when we have multiple algorithms to solve a problem, we need to select a suitable algorithm and by considering these parameters values actually. So to compare all these algorithms, a set of parameters are going to be considered as we discussed earlier. The main parameters are how much memory is required and how much execution speed or a time is going to be considered of. So these are the two measures we will consider to analyze our algorithm so that and to specify the performance of our algorithm. Based upon these two parameters, we will compare all existing algorithms and we will choose the best one actually. Of course, in addition to that, all other factors will be considered, easy to understand, easy to implement, modularization, all other things will be there. But all those are going to be not objective, it is subjective actually. So that's why those are not comparable. I can't say it is modularized, more modularized, less modularized, etc. More considered as it is more understandable, less understandable. It's comparison because numerical values are not going to be considered. But related to this time as well as the space, we have some numerical values, no? So that's why comparison is going to be easily can be done by us. So the performance analysis are going to be algorithm depends upon various elements. First will be whether the solution exists or not first thing. That is exact solution exists or approximate solution exists. We'll discuss various things in our analysis of algorithm further lectures. Even as a last part of this particular course, approximation solutions and importance of these approximation solutions in our various areas of allied sciences can be considered by us. So that's why first we, while writing algorithm itself, whether it is providing that algorithm is providing exact solution or approximation solution. And also whether easy to understand, easy to implement, all these are considered. And also how much memory is required, how much time is required to solve that particular problem. These are the five major issues we will consider. But among all these issues also, to analyze algorithm, the two factors are going to be major two factors are space and times required for that particular algorithm. And all other things are going to be ignored for comparison purpose. Ignored doesn't mean that it won't be considered while writing algorithm. Ignored only for comparison of the algorithm performance actually. So space and time, these two are considered actually. The performance analysis of algorithm is a process of calculating how much space is required to execute that particular algorithm as well as how much time is also required for that particular algorithm. That is, the performance evaluation can be divided into majorly two phases. One is performance analysis and another one is performance measurement. Please identify the difference. Here analysis, it is measurement. Analysis means before implementing on system itself, we will analyze the algorithm. That is machine independent. We will also call it as prior analysis. A priori analysis. APRORI. A priori analysis. Right? So a priori analysis means before implementing on system itself, we will analyze. That is space. Under this category, we will consider how much space it is going to occupy, memory it is going to be taken, as well as how much time is going to be taken by that particular algorithm to get a solution for any problem. Respective problem, any problem means here. For any various sets of data, we will analyze it actually. So this is a priori analysis. This is more important actually. Because after, for example, in real-time applications, after writing the entire program, after executing the program, if you are getting an error which cannot able to rectify by us, and or in other words, it may take more time, in such cases, again, redoing entire process is very, very difficult task. So to avoid such calamities, generally we will consider, initially we will analyze the algorithm itself. If our algorithm is efficient one, then we will move to the implementation of algorithm into any system actually. So that's why algorithm is written on a paper, no? So we need not have any machine. So this type of analysis is machine independent actually. And before writing the program itself, we are analyzing, no? That's why we will call it as a priori analysis also. A priori analysis also. Right? So when we are using this a priori analysis to find the space and time complexities of algorithm, based upon this, various logics are available. Which logic of or which algorithm is best algorithm can be chosen based upon the time taken, space required for the respective algorithm actually. So these two measures are considered by us. Of course, performance measurement is there. Measurement means calculation. This is machine dependent. Once you have written a program, it will be executed. So how much space is occupied by that program? How much time is taken, CPU time and various times are going to be displayed to us while executing the program actually. Of course, various built-in library functions will be there to get all this information. By using this information, we able to get how much time is occupied or how much time is taken to execute that program, as well as how much space is also occupied by that program, memory space. But this is machine dependent. Depending upon the machine speed and depending upon the operating system availability, depending upon the compilers we are using, this is going to be maybe various changes may occur for the same logic of the program actually, depending upon the speed of the computer, etc. So that's why first, as a part of our course, analysis of algorithm is required for us. That is performance analysis of algorithm. That is machine independent based analysis required. Before writing the program itself, we would like to check whether our algorithm is correct or not and how efficient or not. Then we will move to implement it on the system actually. So that's why, as we discussed now, two parameters we have to consider, that is space complexity and time complexity. So what is space complexity? The space complexity of an algorithm is amount of memory it needs to run for completion of the algorithm actually. That is memory space calculation. And time complexity means how much amount of time is it required to run our program or to run our algorithm. How to calculate? Because we are not running on a system. So, but how much time it takes, we have to consider various techniques to get time needed to execute that algorithm as well as space required to process that particular problem also. So first we'll consider the space complexity. So the space complexity of an algorithm is amount of memory it needs to run to completion. That is, if we are going to implement on system, how much memory space is going to be occupied by our algorithm to store our input data or to store our any temporary values, etc. Actually, that means how much memory space is required, this is remember analysis only. Analysis means approximation space. It may have some one or two values may be different will be there. So it's not fixed amount. It's analyzed actually. So the space complexity of any algorithm P is given by equation space of that particular algorithm P is equal to C plus SP of I, where C is considered as a constant. Constant means irrespective of the input instance. Whatever input you are going to provide, this C is going to be having a fixed value. But depending upon the instance, your SP of I is keeping on changing. What is I? Instance, input instance actually. So fixed space requirement C, it is independent of the characteristics of our input and outputs. It includes instruction space. Also, it includes some of the variables used, fixed number of variables used in our algorithm. Simple variables, fixed size, structured variables, constants, and for all of them actually. These are all fixed, irrespective of the instance of input. How much input you are taking. Let us take an example of sorting. When you are sorting an array of elements, array may be 100 elements, 1000 elements, or 1500 elements, or any number of elements. But irrespective of that, your sorting technique may use some additional memory space for swapping or for storing temporary data. For all these things, a memory is going to be used. That is considered as a fixed. Those will come under this C, fixed space constants. And another one is variable space constant. Variable means it depends upon the instance of I. That means, for example, how many memory locations are required? If input size is 100 memory locations are required. Or input size is 200 memory locations are required. Input size is 1000 memory locations are required. Or in some cases, square of the input, n square is required. 10 means 100 memory locations may be required. 100 means 10,000 may be required, and so on and so forth. That means the memory space is varying depending upon the instance of the input actually. That is SP of I, instance of the input actually. So that's why it depends upon the instance of the characteristic I. What is I? I is a input actually. And the number, size, values of inputs and outputs are associated with this I. And also in addition to that, depending upon the algorithm, some stack space can be used. For example, recursive algorithms, if you are using or some other algorithms, internal stack space is going to be used. Formal parameters, local variables, and return addresses. All these are going to be maybe using in our algorithms. All these are considered under SP of I. So what is space complexity? Total how much memory is going to be used by our algorithm. This is having two parameters. One parameter is a fixed value. That is all temporary locations which we are using in our algorithm. Those are independent of the input instance. And second parameter is depending upon the input instance, because input instance is keeping on changing. This SP value is also changing. This is a variable space requirement, which depends upon our input actually. For example, I'll give an algorithm here ABC. By using ABC, we are computing some value. What is element? How much memory space is required? We required input size is also. There is no depending upon how many elements are there? 3 elements only. There is no change in our input instance. Always 3 only. So that's why our SP of I is equal to 0, then what is our constant C? C is equal to 4 actually. C is equal to 4, why? 3 for A, B, C values. And we are returning this value, no, this address, return address may be considered as a 1. So totally C value will be 4. But SP of I is equal to 0 only. Because depending upon the input, there is no any change actually. So that's why in such cases we can consider. We'll take one more example. That is a simple example. Now we'll take some other example. Iterative function of sum of list of numbers. How many numbers? Let us assume that I am reading list of numbers n. I have to n. For example, n is equal to 5. Further, how many elements I am supposed to give? 15, 25, minus 30, 40, 60. Further, 5 elements must be provided maybe. Depending upon the n, list of numbers must be provided and all list of numbers must be summed up. This is our problem actually. That means iteration. How many number of every time I have to read my number, it must be added to my sum. So what is initially we are going to have the parameters which we are passing as algorithmic notation. We are passing the list as well as n. List means list consists of the list of numbers and n is the number of elements in that particular. For example, if n is 10, our list of number consists of further 10 elements. As just now I explained you, 5 elements I explained you. Similarly, whatever n value is there, our list consists of so many values. Clear? Now, so what we are using? The sum variable. Initially, we making sum variable as 0 because we are going to every element we are keeping on adding to this sum variable. So when we are updating it by adding it, then original value must be there. Otherwise, dump in memory will be taken as a first time, which will give an error to us. So this is initialization. So temp sum is equal to initialized to, for I is equal to 0 to n, temp sum, that is, it is repeating. How many number of times it is repeating? N times. 0 to n minus 1, that means n times. N times it is adding, the respective element is adding to the temp sum and return temp sum. How many memory locations are required here for this? How many memory locations? How many memory locations are required? For n is equal to 5, I need first n, 1 location for storing n and 5 locations for 5 elements, further 5 elements, because n elements, no? So to store them, further elements, array, no? Array of 5 elements, array of 10 elements, depending upon the n. And also I am using temp sum to store temp and read. Totally how many? 7. For example, my n value is equal to 10. Then what happens? This is fixed. This is fixed. But here this becomes n. That is totally 12. So instead of taking n value, particular value, I'll take n value as n itself. That means I need totally for n storing n elements is n required. Plus for storing n value, for storing temp sum and for returning that value, I need 3. What does it mean that my SP of I is n and my C is 3. 3 is constant. SP of I is going to be keeping on changing. For n is equal to 5, then SP of I is 5. N is equal to 10, SP of. N is equal to 10,000, SP of I is 10,000. It is variable depending upon the n value. Our space instance is going to be considered. So in the above example, list is dependent on n. So hence SP of I is equal to n, which is a variable space actually. So which is a variable space, and remaining constant terms are to store my value of n, to store my value of I, and to store my value of temp sum. 3. These 3 are fixed. So that's why the time or space taken for this particular small program, that is small algorithm, is n plus 3. N is for storing n elements. 3 is for storing value of n, value of temp sum, and value of I. Totally 3 variables are there, fixed variables, and n variables are varying variables actually. Depending upon the n value, the respective SP of I is going to be changed. So what is my entire space complexity? Space complexity is 3 plus n. So 3 is fixed constant value, n is a variable value actually. So this way we can calculate some of the memory space required for a particular algorithm. Similarly, we can calculate for recursive function also. Of course, for recursive function, stack memory is going to be used as a fixed memory also. Now you observe same program, we are using list and n value recursive function, sum of the list of numbers. If n is less than or equal to 0, then we are returning 0. 0 elements means no need to pass no, so 0 value will be returned. Else return r sum is equal to list of n minus 1 plus list of n. It's a recursive function. For example, n is equal to 5, then it will calculate list of 5 plus n minus 1 means again it is calling for 4. Next, list of 4 plus calling for 3. That is list of 3 it is calling. And so on and so forth. When your value becomes 0, n is equal to 0, then it will stop the process actually. While stopping the process being a recursion, it will work towards the upward direction. That is list of first, list of 0 is added, then 1 is added, then 2 is added, then 3 is added, and so on and so forth. So what are the changes occur depending upon the n, the variable will be there. So it is going to be how many number of times it is recursing. The recursive stack space is considered. It includes space for the formal parameters, local variables, and return address. That means each call our R sum contains 3 locations along with our list also. So that's why at the length of the recursion is n plus 1 times it calls actually. Actually correctly n times only, but n plus 1 times it will return the 0 value. So reversely it starts calculation actually. So as length of the n plus 1, 3 is our fixed location. I'll get 3n plus 3. 3 is fixed locations and 3n times it is calling. So 3n considered to be as a 3 into n plus 1 can be considered actually. So recursive time, recursive complexity, recursive algorithms complexity includes the space required for our stack also. Internally it uses stack recursion. So that's why stack space and its calling, pushing, popping, all these operations complexity will be considered actually. So space complexity will be calculated, but nowadays space is not a that much, considerable things because memory space cost is getting reduced. So that's why nowadays space complexity is not considerable thing for simple problems actually. But in certain cases, space complexity is also will be considered actually. So we have to concentrate majorly on our time complexity actually. Of course, space complexity must be calculated by us, but the cost of the memory space is nowadays is, time to time it is getting decreased, no? So that's why memory space considerations are going to be not that much considerable in business related applications majorly. The time complexity of an algorithm is considered as a second parameter, the major parameter. So the time complexity of an algorithm is amount of time taken to run that particular algorithm. Please remember, it's not a program. We are not going to run on computer directly. It is a machine independent and it is a priori, right? So that's why to completion, it's not on computer. So that's why run to completion of that particular task actually. This is also represented by T of B. Let P be an algorithm. Time taken to complete that particular algorithm or to get the solution for that particular algorithm is T of P. Time taken. We will, in general, if it is a program, it is compilation time and execution time will be considered. But it is not an algorithm, no? So generally compilation time is fixed and execution time is going to be varying. Why? Because what is compilation? Converting our programming language into a machine level language. So n steps are there. We have to convert n steps anytime. For example, if our input is size is keeping on changing, irrespective of the input size, the number of instructions to be compiled is same actually. So compilation time is going to be considered as a fixed and execution time is going to be variable. Why? Because depending upon the input size. For example, to sort 10 numbers, it will take less time. To sort 100 numbers, a little bit more. If you would like to sort 1 million numbers, it will take more time. So depending upon the numbers, that is input size, the time taken to sort the list of elements is more actually. That is, the execution will be more. But the compilation is same because same number of steps to be converted into machine level language. It is constant actually. So the compilation time does not depend upon the instance of the input characteristics. So we will consider our time complexity is also as C plus TP of I, where C is independent of the instance characteristics, that is constant time taken to compile your program, and TP of I is, it depends upon I, instance of input. As just now told you, to sort 10 numbers, how much time? 100 numbers, 10,000 numbers, million numbers. Depending upon the size of your input or instance of your input, the time taken to do the sorting is varying. So like that, the problem or the result of the problem depends upon the size of the input also. So the time complexity is calculated in terms of the execution. But analysis of algorithm, we are considering. That is algorithm. We are not executing on our system now. Then how to get this time complexity? Because time taken to execute the program is not computable by us. Because it's not system, beforehand itself we would like to calculate it. So that's why the time complexity is calculated in terms of the steps of the algorithm actually. Steps of the algorithm means not physical steps. How many number of steps are getting executed? Those steps are going to be executed through tracing. We can consider the number of times the steps are going to be get executed. Depending upon that, you can calculate. Of course, each step need not take uniform time generally. For example, A is equal to 0, take less time. A is equal to A plus B plus C plus D star, something I have given a long expression, it will take more time. That is depending upon the operators used in your statement, depending upon the statement, time taken to each statement may get vary actually. Should get vary in conformly. But what we are going to consider, no? So it is difficult to know the complexities of the individual operators and to assess them. So that's why we will assume that individual statement, whatever may be the complexity of the statement, each statement, executable statement, remember, each executable statement will take some fixed amount of time. For simplicity, we will consider each executable statement take a time of 1 unit. Whatever may be the statement, it may be a simple assignment statement, or it may be a complex print statement, or it may be any complex expression calculation or statement, whatever it may be. We are going to assume that the amount of time taken by each statement is almost same. Based upon this, what happens? We will count number of statements get executed. Remember, not physical number, executed. How many? For example, I am using for I is equal to 1 to n print I. How many number of times this print I executes? N time executes. So, for example, if you are writing for I is equal to 1 to n print I, let us assume that I am using, then basically seems to be how many statements? It may be a single statement. First statement is there. For example, let us assume that maybe 2 statements if you are going to think. That is physical. But executable statement means this print I, how many number of times it get executes it? n times it get executed. So that's why we have to write print I number of times is going to be n times frequency. So that's why each statement is considered to be as a 1 unit of time it will take, and how many number of times that particular statement executes, that is the frequency of the statement, must be considered by us, so that we to find total number of times or total amount of time to take in to execute that particular statement is considered. So we will consider frequency, number of times a statement is getting executed. Now we will see 1 or 2 examples how to calculate the time complexity by using a simple notation known as tabular column method. For example, this is the algorithm we have considered. Previous example only I am considering. Sum of the list of elements, and each 3 columns I am using, right? So statements per execution. Once it is getting executed, how many statements are going to be, how many times? Frequency, how many number of times the respective statement is getting executed. By multiplying these two, I'll get total number of statements. And when we are adding them, I'll get a total number of executable statements, which will give the time taken to that particular, same as our time required actually. That means here, for example, algorithm sum of list of n. So this is not an executable declaration. So 0, no frequency. So 0 only. And we will consider open parenthesis, it is not executable. So that's why 0. And it is also 0. We are getting temp is equal to sum. Is it executable? Yes. So 1 executable statement. How many number of times it get executes? 1 time only. So 1 into 1, 1 I am getting. Next, for I is equal to 0 to n, do. So for I is equal to 0 to n, do means we are going to have, this is for this one, and this is for this one, and we are using, this is for this, and we are considering this, right? So now for loop, how many number of times it get executes more? For loop is going to be get executed n plus 1 time. For I is equal to 0, get incremented, I is equal to 1, I is equal to 2, I is equal to 3, etc. Up to I is equal to n minus 1, it will execute within the for loop. But it will reach I is equal to n plus 1, n minus 1 also, n also. So that's why total number of times executed your first statement is going to be n plus 1. Why? Because your I takes value 0, 1, 2, etc. up to n. Up to n minus 1, it will execute your loop. When it reaches n, then it will come out of the loop. That means for I is equal to statement get executed n plus 1 times actually. Right? So that's why one executable statement, if you want, you can consider it as a n plus 1 frequency. By multiplying this, I'll get this one. Next, within the for loop, what is there? Temp sum is equal to temp sum plus list of I, one executable statement. But how many number of times it executes? Within the loop, no? So n times it will enter the loop. So it will n. Next, after a for loop completion, it will come to the return. Return is 1 time executed, 1 statement. So frequency is also 1. Closing parenthesis, not executable statement, 0. So 0. That is, total executable statements have been written here. We will sum up, we will get 2n plus 3. That is, total number of executable statements are 2n plus 3. Therefore, our time complexity is of this algorithm can be considered as 2n plus 3. So 2n plus 3 means it depends upon our n. If n depending upon the n increases, automatically your time complexity keeping on going on increasing actually. This is called as a tabular column method. In tabular column method, 3 columns I am using. For each statement I am finding whether it is executable, how many statements are per execution will be considered, and how many number of times it get executes as a frequency. By multiplying the respective statement values of these two, we will get total number of times, and by summing up all these total statements, we will get the time complexity. Remember it, even though it is a frequency or executable statements, how many number of times it is getting executed, if you are considering, even though we are considering that only, but each statement we are assuming as almost take the same time. One more example, recursive sum is there actually. Remember, same we are considering. Here we are returning. So, how many number of times it is executing? X. X times it is returning. So, into X, 1 plus X into 1, depending upon the frequency, the respective total 2 plus 2 into 2 plus X is going to be considered. Matrix addition you take now. Matrix addition means rows and columns. Remember, we are considering only reading, writing I am not considering, because reading, writing means we are passing the values as parameters, being a method. Only logic is used. To execute your matrix, row for one loop for rows, another loop, inner loop for columns, and for I is equal to 1 to m number of rows, and for j is equal to 1 to n number of columns, C of ij is equal to A of ij plus B of ij. Respective elements are added. As now we will calculate how many number of times it get executed. This is going to be 0. This is also 0. For I is equal to 1 to n means one time only, but frequency is m plus 1 as we discussed earlier. Remember here also for j is equal to 1 to n means it is how many number of times? It is within the for loop of m. So that's why basically it is n plus 1 only, but m times n plus 1 is get executed. So m into n plus 1, and the Cij is getting executed n times inner loop into m times outer loop. So mn times as the frequency. When we are multiplying each statement by its frequency, I'll get 0, 0, m plus 1, mn plus 1, mn, which is equal to 2mn plus 2m plus mn. Let us assume that I'll consider m and n are, instead of different variables, I may consider variables of the same. Let us assume that n. It will be considered as a 2m into n means n square. You can consider generalization. 2n square plus 2n plus 1. This can be considered as a quadratic form. So that means here the expression which I got of order 2, please remember, for one for loop order 1, nesting of for loops, 2 loops are nested order 2, right? Nesting of 3 for loops order 3 will be there. So depending upon the loops are going to be get nested, the complexity order is going to be increased like anything. So that means here whenever we are analyzing runtime, it depends upon n and machine, language, compiler and program. But instead of that, algorithm when we are considering, we are using only n only. So that's why we are going to consider this complexity is the time complexity of nesting of the 2 loops. We will make more generalized in the next video, so that asymptotic, that is more generalized, and growth, rate of growth functions are going to be considered by us, so that more generalized time complexity can be represented by using this asymptotic notation. But whenever we are executing such a program or such an algorithm, we have to consider various cases or kinds of analysis, we will call them as. That is the worst case complexity, best case complexity and average case complexity. Worst case complexity of algorithm means defined as the maximum number of steps taken on any instance of n. So how much maximum number of statements are getting executed, that is the worst case. Best case means how much minimum number of steps are going to be executed for any instance of n. Then for a particular instance of n, then we will consider it as a best case. Average case means average number of steps are getting executed for any instance of n. Worst case generally happens maximum time, and best case happens the minimum time on some input it will take. Average case means expected time of algorithm over all types of size input n actually. Calculation of average case is very difficult, but some statistical distribution is there. But we need to concentrate upon most of the time average case only. Why? Because best case is generally useless, not necessary. For example, I am searching for an element. If the element is first element itself, it will take only one comparison. It's a best case, but not necessary. It need not be verified by us. Only one comparison only. Even worst case also. Searching is unsuccessful means worst case. It is a pessimistic. Most of the time, worst cases are also not that much useful. But most of the time, average cases are going to be used, and we have to find the average cases. Even though it is very difficult, we have to identify in a proper manner. Of course, in some cases, worst case is also required. For example, traffic control, surgeries, worst cases are required. Worst case, how much time it is taking to do that particular surgery. So, how much minimum time is required in traffic control, the lighting, your traffic lights, signal lights are going to be on the same signal. How much time, minimum time is required. These are required in some applications. So, knowing these worst case complexity is important or crucial for some applications. But most of the normal applications, average case analysis is more useful to us actually. Because worst case, generally we will consider pessimistic thinking, but of course not always. As I told you just now, some applications, traffic control system, surgeries, there we need worst case analysis is required actually, right? So, but normal applications, in most of the applications, worst case and best case are not that much useful to us, but average case is more useful to us. So that's why till now we discussed various kinds of analysis which time complexity and space complexity is to be calculated. But by using our tabular column notation, if I am calculating the time complexity, that is running time, it depends upon input size. But we are getting various types of expressions we are getting, so that how to compare them actually. So that's why this parameter is in running time by size of the input, it's okay. But short sequences are easier to sort than longer ones. So that's why generally we will use some upper bounds. That is the maximum value it is considered on the running time, so that everybody likes, okay, some solution is guaranteed. So this is the maximum time. Within this particular time, solution is guaranteed. That means we have to consider the running time must be considered as based upon the some lower bounds and upper bound concepts by comparing the algorithms of running times as a function of two functions, function of n, function of g of n, f of n. Two functions we will consider. So we will rough measure which characterize the how fast each function is going to be growing actually. That is, we have to use the rate of growth. So depending upon the rate of growth function, we will decide whether f of n is more considerable algorithm or g of n related algorithm is more considerable by us. Use rate of growth comparison we have to consider. That is, we have to compare the functions in the limits which is asymptotically. That is, asymptotically means for larger values of n, going on increasing n value, how our function is going on increasing, what is the order of growth will be considered. Based upon that, the comparison is going to be carried out. Fine. We'll discuss about these asymptotic notations in the next video, and also we will compare various algorithms, how to find these time complexities and space complexities for all three possible cases, that is kinds of analysis: worst case, best case, as well as average case. Thank you. Thanks for watching this video.
Like, share and subscribe. Hit the bell icon for more updates.